Okay, to start the final part of this lecture on the activity of the sun, then I had a couple of things for you to go and look up. The first was to find out where in the current solar cycle we are. So there's a number of ways to do that. But one site you can find to do this is the Space Weather Prediction Center from NOAA in the US, who have a nice diagram like this. And so here we are at the current time, and you can see that we're basically at a solar minimum. So the sunspot number just starting to creep up again. So we're quite an interesting time actually. So between the flip over between two cycles. Okay, so we're about to start what they would call cycle 25, and we're just leaving cycle 24. So the last maximum was back in around about 2014. Okay. And the other task was to go and look up a site that tells you what the sun actually looks like today, or it's close in time to today. This is when I looked it up. So this is quite a nice site. There's quite a few of these sites, but this one has a lot of nice images all together. So multi-wavelength images of the sun for basically now. And so you've got the typical optical picture. And commensurate with the fact that we are actually at solar minimum, then actually there's very little going on in terms of sunspots in pictures in the optical here. So you can see the wavelengths here. Sorry, these are in old-fashioned angstrom units, but that's 617 nanometers. So these are optical pictures. Here is another of these magnetograms, so showing you where there's any magnetic field measurements going on. And here you can start to see hints, even though this is measured in the optical, you can start to see hints of a grouping here. So you've got white polarity leading the black one here, and actually a hint of another one down here with the opposite polarity, as we discussed. And it's only really when you go to the extreme ultraviolet here, so hundreds of angstroms or 17 nanometers, 19 nanometers, and here is the actual X-rays, so even further, just a few nanometer wavelengths. Here you can start to see there are some active regions there. So this is this active group that you can see in the magnetogram here, and hints of this other group down below here. So that's what the sun is looking like this week, basically. So not a lot going on, but there's always something going on. And here you can see these coronal holes as well, again, without any coronal emission. Okay, so last time we saw this, strange cycle of activity going on with sunspots, the 11-year peak in the maximum number, the patterns of polarity, the butterfly diagram, drawing the spots down towards the equator over time, and the polarity flipping every 11 years, giving us a 22-year cycle in total. So how can we explain all of this? Well, the general idea is that the sun acts as a dynamo, so there's basically a strong magnetic field, and the sun generates its own magnetic field. It's not some fossil field left over from the formation of the sun, so that the magnetic field is constantly being regenerated. And it's very similar to, in a sense, the principle of a dynamo here on the Earth, where you get a coil of wire, and you maybe have a bar magnet, and you rotate that coil of wire in the strong magnetic field, and that generates a current in your coil. That current then will generate its own magnetic field, which then interacts with the other magnetic field. So you need a combination of kind of rotational measures, currents, that kind of thing. And so you can set that up in the sun because we've got this kind of complex three-dimensional motion of a plasma, and a plasma can conduct electricity and therefore also interact strongly with a magnetic field. So we've seen those two types of motion already. You've got the differential rotation of the equator moving faster than the rest of the higher latitudes in the sun. So that's in one direction. Then you've got the convection, which is going up and down vertically in the outer layers of the sun as well. So that combination of sort of three-dimensional motion in the plasma will give you, generates a dynamo action which generates the strong magnetic field. And it's especially strong around the equatorial regions. Now, this is where the differential rotation comes in, because as we shall see in the diagrams, this acts to sort of stretch out and twist up over time the magnetic field lines. Okay? So you can kind of think of magnetic field lines a bit like, you know, sort of very long elastic bands that you can stretch them. Okay, so if they're anchored into a charged gas and that gas is moving, it will draw out the magnetic field lines and move them around. So over time, if you started with a simple magnetic field, it'll get twisted up. And eventually you get sort of tension in these magnetic field lines, again, very much like a sort of very twisted up elastic band. And that can cause the field lines to arch up into the atmosphere of the sun. And that generates those loops, those bipolar pairs that we see as the reason for causing the sunspots, because then you've got these loops with the vertical magnetic field at each end, which causes the cooling in the photosphere. So let's have I've got a few diagrams here attempting to explain this. It is rather complex, difficult to visualize a little bit. So let's start on the left-hand diagram here. Again, this is from the old textbook. So here, imagine starting with a magnetic field line that was going vertically, you know, from along the rotation axis of the sun. But as we've seen, you've got differential rotation. Okay, so the equator starts moving around faster than these higher regions, and so you start to shear the magnetic field line here, and it will draw the magnetic field line out that way. So even if it started vertical, it will start to draw it out horizontally. So that's the differential rotation going this direction. And of course, underneath all of that, you've got the convection currents as well, which are also acting to twist the magnetic field up and generate the magnetic field through the dynamo action this way. So that's one way to look at it. Here is another sort of simplified diagram, really, to try and indicate what's going on. So imagine, again, you start with a simple, what you would call a dipole field, so very similar to the kind of magnetic field pattern that we think we have here on the Earth, okay, where most of the field lines are actually starting out vertically in the sun, okay, aligned with the rotation axis. But over time, this drawing out action due to the differential rotation will start to wind up the field lines, and so that will draw them out like this, so they end up in the equatorial regions becoming aligned more to the equator. So they've gone through 90 degrees here, and they're getting twisted up, twisted up, twisted up in these directions. And eventually the tension in these lines can get so strong that they start to buckle and twist and arch up, and so you generate these loops, okay? And it's these loops that then protrude out through the surface of the sun and start to cause the sunspot pairs. So that sort of indicates how you might get sunspot pairs. And you can see here, due to the way that this has happened, that you've got opposite polarities of these pairs in each hemisphere of the sun. So the next diagram, I think, shows that a little bit better. Okay, so here's another diagram. This is from the universe textbook. So again, the same thing, the field lines being drawn out in the equator and twisted up, and eventually you get these arching up pairs like this. And you can see, because of the direction of the magnetic field, okay, it's going this way in the upper hemisphere and the opposite direction in the lower hemisphere. And so that explains this pattern of bipolarity that we see in the actual real sunspots. So here you've got the north leading the south in this hemisphere, and you've got the south leading the north in the other hemisphere. So that explains the idea of the kind of phenomenology that we see. This diagram also, well, maybe not quite showed, but over time the twisting up also tends to draw the sunspots closer and closer to the equator as well, but they never get to the equator, and you can kind of see that in this diagram here as well. Okay, so what about the polarity flipping at 22 years? Well, here something remarkable happens in that the entire sort of global structure, the overall structure of the sun's magnetic field really does flip over every 11 years. Okay, so you might start off with the magnetic field lines going vertically in this direction. They get twisted up, twisted up, twisted up so much that at some point the tension in the field lines is so great, and that's when the magnetic activity is at its height. You've got the maximum in the sunspot numbers and all the activity going on, that the only way to relieve all of that tension is for the entire magnetic field pattern on the sun to flip over, so that what was previously the north magnetic pole will flip over and become the south magnetic pole. And at that point, everything untwists itself, and effectively the whole thing starts again. You'll start again with a simple, mostly vertical magnetic field, but this time flipped over, and the whole twisting process starts all over again, and you're into the next cycle, but this time with the reverse polarity pattern that you had in the previous cycle. Okay. And so we can see that in action here. So let me just, there's a nice little movie here. So we'll just go over to that. And let's put it back to the beginning and stop for a minute. Pause it. Okay. Just move myself out of the way here. So the coloring here represents the sort of global polarity of the magnetic field lines here. So you see you've got all the complicated structure in the equator, but at the poles where you've got the open field lines, you've got this general kind of idea of vertical magnetic field going on here. So you'll see at the beginning they're calling them positive and negative here instead of north and south, but here you've got the green positive magnetic field in the at the north of the top of the sun, and the purple ones at the bottom. Okay, so this is going to flip forward quite quickly. So after it's going to run for about 12 years. So this is real data over 12 years, and you'll see quite quickly that the purple regions of the magnetic field flip over and move to the top. Okay. So you can see it's very, very active, very complex. But here we go. You can start to see it's getting mixed up, and now suddenly purple is dominating on the top and green is dominating at the bottom. Okay, and so you can see that there was a flip there, and so that's when the whole polarity pattern changes as we get it starts to head back. You can see it's getting more complex there at the end as well. Yeah.
Scientists claim that the Earth's magnetic poles will actually reverse within the next few thousand years.
Yeah. That's the problem with YouTube, I find. Yeah. Okay, so, but you know, you can go and follow that link and have a look yourself. Okay, so you know, you might think this is a bit weird, but actually the same thing happens with the Earth's magnetic field. So on a much longer time scale, and not with any regularity really, but over geological time scales, you can see, looking at sort of cores, but geological cores going back in time in the Earth, that the Earth's field has flipped many, many times over geological time. And it's actually quite a similar thing going on in the molten core of the Earth. Okay, so let's summarize all of this. So, so the sun has this very complex magnetic field that you've just sort of seen there, but that really generates, so you've got this dynamo going on and controls all of the activity we see. So all of this phenomena that we see, the sunspots and all the related corona activity. It's generated by the differential rotation and convection. That's what generates the dynamo, which gives rise to the strong magnetic field. And we'll see in a moment. I'm going to show you a few more movies. The corona generates very high energy activity. And so again, it's not really part of the module so much, but you can read a little bit about it if you like. So you get these so-called solar flares. So when the magnetic field gets twisted up, sometimes it will reconnect and shoot off a lot of plasma out into interplanetary space, and that goes all the way through the solar system. So you get basically the solar system is bombarded with high energy particles coming out of the sun because of all of this activity. So so-called coronal mass ejections, solar flares, all of that type of activity. And again, that has an effect here on the Earth. So it gives rise to the kind of space weather. So sometimes this can be quite bad. You've got charged particles that come down and can even knock out sort of satellites and even power generation networks on the surface of the Earth. More prettily, really, you get the aurora at the north and south magnetic poles of the Earth, where the charged particles give rise to these beautiful lights in the sky. So I'm going to show you a few movies now. Again, they all come from the SOHO satellite, so you can follow this link here and go and see some more of them if you want. Okay, so the first one this is going to merge in a moment into a multicolor image of the sun, so that you can see what's going on. Okay, and so here we are over time, and so you can see these active groups and the big loops here being constantly changing over time. You can see the size of these. So again, this gives you an idea of the extent of these loops that arch way up into the atmosphere. The next one is a little bit more detailed. So again, this is from extreme ultraviolet wavelengths, so you can start to see these loops here. So you've got these very active regions here, and so if we play this, you can see it's just a constant barrage of activity here. So obviously this was a very active time. You can see more loops coming over the surface here. Keep an eye on these. You get sort of big explosions like lightning strikes almost every now and again, like here. So you can see them going off there. So that is when high energy particles, you can see gas moving around the loops quite quickly here. Okay. And again, just flaring away here, a very active region. And as you can see, that it's starting to eject stuff way out. You've got these big loops that sometimes just reconnect at the bottom, and they open up and then eject material into space. Let's play that one again, because it's very dramatic. Okay. So these events would be solar flares. You can see another region down the bottom here. And these structures are enormous, right? So each of these loops, you could fit the Earth quite easily just in one of those loops. So these are big, powerful events. So that's what's going on, right down close to the surface of the sun. In the last movie here, I'll just explain what's going on. We're sort of taking a step back. So again, this is from the SOHO satellite, which has been up there for many, many years now, monitoring, very successful European satellite. So here now, the actual photosphere and the whole region around the sun has been blocked out by this dark disk that you can see that's held in place on this rod here, if you like. So where the sun is would be where that white circle actually is. That's where the photosphere is. But we're blocking out all of that. So basically it's called a coronagraph, because it's allowing us to see the corona now. So it's just like during a total solar eclipse, where instead of using the moon to block out the sun, we're actually, this is a satellite in space. So it's got this artificial disk to block out the sun's photosphere so that we can actually see the corona and really see what's going on. So all of these little points of light around here are actually just background stars. In fact, this I think is the planet Venus. You'll see the star background moving along in the background. But the thing to keep an eye on is all this coronal emission here. So this is now the white glow of the corona that you would see during a total eclipse. But of course here we can see it all the time, because this is constantly blocked out. So we can monitor this activity. So this is going, many, many solar radii out into space now, and you'll see how dynamic it is. Okay, so you're getting these so-called coronal mass ejections happening every now and again. So that's huge explosions, effectively. Ejections. So these fast-moving charged particles, then so mostly in the equatorial region here, not much coming out this way. But of course, this is also the orbital plane of the planets. You can see Venus here, and obviously the Earth is in this plane as well. So all of this kind of material is ending up flying out through the solar system. So that's what gives rise to what's called space weather. So clouds of high energy charged particles hurtling through the solar system. So these kind of moving at many thousands of kilometers per second. So they just take a short time to reach the Earth. So you don't have too much time to prepare. I mean, you have enough, but if there are astronauts in orbit in the space station, for instance, on a spacewalk, you keep an eye on this kind of activity and bring them in if one of these flares has taken place. Okay. So, as I said, you can follow more of those movies at the ESA site. Also, the TRACE satellite will have some more of these as well. Okay, so I'll leave you with one more exercise for you to have a go at and have a little explore of this idea of the differential rotation, which you see is sort of key behind a lot of this explaining the solar cycle and the sunspot activity. So I mentioned this idea that the rotation period for a sunspot near the equator of the sun is shorter than the one further up, at higher latitudes. So just have a little go at working out how long it takes for the equatorial spot to basically overtake, to lap, if you like, if you want, a bit like runners on a track, to lap the one coming from the higher latitudes. Okay. So the one will go ahead of the other one. So how long before it comes back and overtakes it again? Okay, so let's leave it there.